So now in the last lecture we have derived the expressions for VIH, VIL, VOH and VOL. Now we'll focus our attention of finding the DC power dissipation for a resistive load NMOS inverter. So this is BVLSI lecture number 41 online, and today's date is 7. So let us find DC static power dissipation for the resistive load NMOS inverter. Okay, let me draw the resistive load circuit once again very quickly. We can draw 3 terminal also, no problem. So here is my input applied, here is my input, here is my output, and here is my VDD. This is RL. Okay, this is IRL, this is ID. Alright, this is my resistive load NMOS inverter. So there are two cases to consider for finding the DC static power dissipation. For the first case, input is low. Input is low means VOL, very low. Okay, in the second case, input is high. Input is this much high, VOH maximum. Okay, so let's start with case number 1, case A, when input is VOL or low value, very small. So when input is low, that means what? V in is VGS. That means this is VGS is less than VTO, right? My NMOS will be in cutoff mode. So if my NMOS is in cutoff mode, what will be my drain current? ID off will be 0. Okay, so since the ID off is 0, my power dissipation in the circuit, which is VDD into ID, will be 0. So power DC or P average is 0 when the input is very low. Understood? So it is 0 when input is low, very low, lesser than VTO. VTO is the threshold voltage of NMOS. Remember this. Now we'll consider the second case. Case B, when input is VOH, very high value. So definitely VGS is greater than VTO. Okay. So when the input is high, your driver MOSFET is on and it conducts the current ID. Okay. So we are not checking the state right now. Your driver NMOS is just on. We don't know whether it's a linear or saturation, and the ID current flows in the device, right? So here the output voltage in this case is equal to VOL. Why? If we draw the VTC curve, this is my V in, this is my V out. So when V in is very high, if you see over here, notice one thing, V in is very high, let's say close to VOH. What is my output level? Very low. So almost equal to VOL. Yes or no? So here output voltage V out is almost equal to VOL when input is equal to VOH, high value. That's the inverter, right? Now, so ID will be equal to IRL, which is VDD minus V out upon RL, according to the formula, right? IRL is VDD minus V out upon RL. Now, so V out is nothing but VOL. So it will be ID equal to IRL is equal to VDD minus VOL upon RL. Okay, so this is the formula. This we call it equation number 1. Now assuming that input voltage is low during 50% of the operating time and high during 50% of the remaining 50% of the time, then the average DC power dissipation of the resistive load NMOS inverter can be, so this is current, right? So we are assuming 50% it is on, 50% it is off. So power will be, of course, has to be VDD into ID, right? But since we are assuming 50% of the time, it will be VDD by 2 into VDD minus VOL upon RL. Understood this? So this is the power dissipation formula for a resistive load NMOS inverter. Why we are written VDD by 2? Because we are assuming that input is low for 50% of the time. Input is low for the 50% of the time, and input is high during remaining 50% of the time. That's why we are calling it as VDD by 2. VDD by 2. So the DC power dissipation in a resistive load NMOS inverter is VDD by 2, VDD minus VOL upon RL. So note down this formula. Now we are solving one numerical. Quickly please note it down. Can we start with the actual numerical now? Hello? Okay, let's start. So write down the question along with me. This is a formal numerical which they ask you in the exam. Consider a resistive load NMOS inverter circuit with VDD equal to 5 volt, Kn dash is 20 microampere per volt square, VTO is 0.8 volt, RL is 20 kilo ohm, and W by 2 is 2. Okay, calculate VOH, VOL, VIL, VIH found on the VTC curve. Hence find noise margin levels and static power dissipation of the circuit. PD stands for power dissipation. So basically we have a resistive load NMOS inverter with the following parameters. VDD is given, Kn is given, Kn dash is given actually, 20 microampere per volt square, VTO is given, RL is given. We have to find the noise margin levels and also the static power dissipation. Can we start? Everyone ready with me? We can start with the numerical now. So keep your calculators in handy nearby so that we can. So please write along with me so that you don't lag behind. Let's start with the solution. So the first term we will calculate Kn into RL because this will be repeated many times. So tell me what is Kn? Kn is Kn dash into W by L. Okay, this is 20 micro into W by L is 2. So this will be 40 microampere per volt square. Kn. Kn into RL will be what? 40 into 10 is to minus 6. RL is 20 kilo ohm. So 20 into 10 is to 3. This comes out to be 8. And the unit is per volt. Okay, V raised to minus 1 actually we can write. Unit. So Kn into RL is 8. This will come in handy later. Next thing we find it VOH. What is VOH? In case of resistive load NMOS inverter, come on tell me. VDD. So VOH is equal to 5 volt. Getting it? Yes or no? Hello? Can you just tell yes or no so that I can continue? You all are finding these parameters. Next is VOL. VOL, we have big quadratic equation which you might have to remember. This is VOL minus twice VDD minus VTO upon 1 plus KNRL into VOL plus twice VDD KNRL equal to 0. Okay, this expression, if you don't remember, you have to derive it quickly. It will take 1 or 2 steps only to derive this, as we have seen in the last lecture. So I calculate unknown value of VOL. So VOL square minus twice, what is VDD? 5 volt. VTO is how much? 0.8. And Kn into RL is, just we have found out, 8, 1 upon 8 into VOL plus 2 into 5 divided by 8 is equal to 0. So you got VOL square minus, substitute this in calculator, it is 2 times 5 minus 0.8 plus 1 upon 8. That comes out to be 8.65 VOL plus this is 10 divided by 8, that is 1.25 is equal to 0. So solve this quadratically and we get two values of VOL. VOL is 0.147 volt. Okay, what's the other value? Can you tell me? You have calculated, na? Calculate this with your calculator and let me know the other value. Yeah, I'm waiting. Point 147. Other values how much? Come on, tell me. You must have got two equations, na? Two values of VOL. So what's the second value? Can VOL be beyond power supply voltage? No. So we discard this and we select this value. Yes or no? So how much is VOL now? 0.147 volts. This is VOL. Next we calculate VIL. VIL. So VIL is straightforward. VIL is VTO plus 1 upon KNRL. That is what we have seen before. So 8 plus 1 by 8. That comes out to be 0.925. So VIL is 0.925 volt. Calculated? Now we have to plot this point on the VTC curve. तो तुम्हें ये भी करना है कि we have to find out V out at V in equal to VIL. So you have to find out V out at V in equal to VIL. That formula is VDD minus 1 upon twice Kn into RL. That is 5 minus 1 upon 2 into 8. How much is that? 4.9375. Yes. So V out at V in equal to VIL is this much. Why we require this, I'll inform you when we actually get this completed. VIL, you have got the value? Yes, no, what? Hello. Okay. Anyways, I will let you know the value. These are the tentative values which we are getting. Of course, almost correct until you prove us otherwise by solving. Then next is VIH. So VIH, directly the formula is there. VTO plus square root of 8 by 3 VDD upon Kn into RL minus 1 upon Kn into RL. So VTO is 0.8 plus square root of 8 by 3 VDD is 5 and Kn into RL is 8 minus 1 upon 8. So plug in these values in a calculator, you will get VIH as 0. Oh, not 0 0.1 point something, 1.9659. Okay, this is the value of VIH. This is the formula which we have to use. Now we have to find the corresponding V out value when V in is equal to VIH. Wait a minute, you will understand everything. Just hold on. Completed up till now? Alright, got the value of VIH. Now we have to find the value of V out at V in equal to VIH. That will be square root of 2/3 VDD upon Kn into RL. Yeah, tell me. 5 upon 8. How much is this now? Can you tell me this number please? At V in equal to VIH. Can you tell me this number? This is 1 upon 4. So 5 upon 12. Square root of 5 upon 12. How much is this? Yes, 0.6455 volts. Absolutely correct. Now, you remember they have asked us to locate these points on the VTC curve, right? So now we will be drawing it on the VTC curve, all of them together. So here is my VTC curve. I'll draw it slightly bigger. This is V in, this is V out, and this is my VTC curve. Here it is. Okay, so this is 5 volt, this is VOH equal to 5 volt. Alright, where is my VOL? VOL is over here. How much was that? 0.147, right? This one, this point. And wherever the slope cuts, minus 1 on the slope, it will be VIL property, and here also it will be VIH. Okay, we extrapolate it down. Correspondingly, we find the value of V out when V in is equal to VIL. Here also we'll find VIH, and corresponding at what value you got achieved this fact. So that will be what value of VIL you have over here when VIH for V out. when V in is equal to Vi, so what is V out? Now tell me the answers. What are the answers? How much is VIL? 0.925. This is 1.959657 volt. Yes or no? And what is the corresponding value of V out over here? 0.655. Here, how much it is? 4.9375. Did you are understanding this? Here we have VOL also. VOL is this. Yeah, correct. Are you following how to plot this now? Yes, no? Okay. So these were the parameters which we have found out. Next is the location of 4 critical parameter on the VTC curve. Next is noise margin level. Please help me out with this. Sixth. Can you help me out in noise margin levels? Noise margin low is given by VIL minus VOL. Noise margin high will be given by VOH minus VIL. Okay. So how much is VIL we got? 0.925 volt minus 0.147. What किया? The 0.925 and 0.147. How much is this? Yes. Next case, VOH is 5 volt and VIL is 1.9659. That is equivalent to how much? 3.034. Okay. So these are my noise margin levels. As you can see, they are extremely biased and unequal. They are not at all symmetric. So asymmetric noise margin levels will always trouble your systems. So noise margin found here are quite low, and it will lead to an misinterpretation of input signal levels. Okay. What is the last thing which we have to find out? You got this answers only, right? Next is 7, power dissipation, PDC, it's VDD by 2, VDD minus VOL divided by RL. Yeah, tell me. Here it is minus VOL. This is 5 by 2 into 5 minus 0.147 upon 200k. So let me know the answer. Hello, I'm waiting for an answer. Is it 60.66 microwatts? Yes, yes, correct, correct. 60.66 microwatts. So this is the way we can solve a numerical on the they will give you the parameters and you are asked to find the 5 critical voltages. Sometimes they even ask you the design question. So now we'll solve one design question and we'll leave for the day. Okay. So one more numerical. Are we ready? So second, both the variety we can found. So write down design a resistive load. Design a resistive load NMOS inverter to meet the following specifications. For the following specifications. VOL is given as 0.2 volt. PDC is given as 200 microwatt. VDD is given as 5 volt. VDO is 1 volt. And muon Cox. Muon Cox value is given as 100 microampere per volt square. So we have to design the resistive load NMOS inverter following these parameters. Let's draw it quickly. Resistive load NMOS inverter. Drawing 3 terminal symbol. So here we have the input and here we consider the output. This is VDD. This is gate drain source. So they are saying now that we have to design a resistive load NMOS inverter. That means what? Design means what? Finding the unknown values. So now finding the unknown values of what? Finding the unknown values of RL. Then we have to find the W/L ratio for the inverter, for the NMOS driver. So this is NMOS driver. So we need to find the unknown value of RL and W/L ratio of the inverter. Can we start? Hello. Can we start with a numerical? Okay. First, we'll write down the formula for power dissipation. It's VDD by 2 into VDD minus VOL upon RL. That will be, you have to find RL now. So RL will be equal to VDD by 2 into VDD minus VOL upon PDC. Okay. Now let's calculate RL. VDD is given to you, yes. It's 5 by 2 into VDD is given to you 5. VOL is given 0.2. PDC is given 200 micro. So load resistance value should be how much? Tell me. Calculate this and let me know. It will come close to 60 kilo ohms. Is it not? Hello. Calculate please. Are you getting 60 or 600? 600k or 60k? Fast, come on, tell me. Hello, hello. Is 60k alright? Okay. Let me draw something, that is the VTC curve, and point out an important observation over here. So since they have given the value of VOL, that means they are sure that this will fall in this range. This is VOL. Okay. So when Vin is equal to, when output is equal to VOL, that is very very small, what happens to the input now? If output is given as VOL, if output is equal to VOL almost very very small, so the input voltages is what? This is output now equal to VOL, correct? So what about the input? When that happens, when input is almost equal to VDD or VOH, agree or no? Yes. So we can say at Vout equal to VOL, input Vin is equal to VDD or equal to VOH. Okay, that means my NMOS transistor is in which mode? Come on, tell me at least this. NMOS driver is in which mode of operation? Output is less, almost very small, right? When output is less, output is VDS. So VDS is less only in this condition. It's lesser than VGS minus VTO. So my NMOS transistor is in linear region of operation. And during steady state condition, we can say IRL is equal to ID linear, which is VDD minus Vout upon RL is equal to Kn by 2 twice VGS minus VTO into VDS minus VDS square. Okay, now you substitute the following values over here. So put Vout is equal to VOL, correct? It's a very low value we are finding out. VGS is equal to Vin is almost equal to VDD, and VDS is equal to output is equal to almost equal to VOL. Okay, so after substituting, what do we get? That is, this is what do we get? VDD minus VOL upon RL is equal to Kn by 2 twice VDD. VGS is VDD almost minus VTO. VDS is output, which is VOL. So into VOL minus VOL square. Okay. So from here we have to find the value of Kn, small kn, that will be twice VDD minus VOL upon RL into twice VDD minus VTO into VOL minus VOL square. Alright, now let's substitute the values over here. Kn is twice into 5 minus 0.2 divided by, this is 60k, this is twice into 5 minus 1 multiplied by 0.2 into 0.2 square. Okay, this is the value of Kn. Solve it further, you will get it as 9.6 upon 60k into 1.56. So the value of Kn, it's 102.564 micro Weber, or sorry, micro ampere upon volt square. Alright, so what do we get from Kn? Kn we want to find W by L ratio. So Kn is, okay, wait a second. You have to find W by L ratio. So Kn is mu n Cox W by L. So what is mu n Cox given to you? Mu n Cox is given to you 100 microamperes. So this is equal to 100 microamperes into W by L, which is equal to 102 microampere. So now we can find the value of W by L. So W by L will be 102.564 divided by 1000, divided by 100 micro. So micro gets cancelled, and what you get is almost equal to 1.2 or 1.02 actually. Almost equal to 1. So therefore the sizing of the transistor should be done in such a way that W by L ratio should be 1. Okay, and now we have to draw the designed circuit. So write down finally designed resistive load NMOS inverter is given by this is gate, this is input, here is my output, and this is your VDD level, this is RL. So here RL value, W by ratio is how much? 1. RL value is how much? 60K. Okay, so this is my designed circuit. Arrow is inward, sorry. Alright, this is my designed resistive load NMOS inverter circuit. In the exam, if they ask you, you have to draw the circuit and find its value of W by L RL. So these are the two categories of numerical which they ask you. So yeah, mostly that's it for today, but there are two more terms which I have to make clear. So you got the value correct? Yes or no, tell me. All the values are fine? Yes, no, what? Now there are one thing which I want to inform you all. We have just an information, it will hardly take 2 minutes. Yeah, the first is the impact. This you will get in the preparatory documents. Impact of Kn into RL on the VTC curve. Okay, so these are the VTC plots for the different Kn into RL values. So as you can see, the higher the value, the more closer it is to the steeper curve. This one, as you can see, and the lower its value, it's much away from the output becomes low. So for a larger Kn into RL value, the output VOL becomes smaller and smaller, and the VTC curve approaches the ideal inverter value. So we should select ideally a large value of Kn into RL. Here 8 value is more closer to the ideal value. Okay, we have a very large transition slope. To achieving large Kn into RL, it's a design headache because we have to also involve the trade-off between the area, which is W into L, power dissipation of the circuit. But your Kn into RL term decides the shape of the VTC curve. It is a critical parameter in the expression of VOL, VIH, VIL, right? All the expressions contains Kn into RL term, and it's an important design parameter which can be adjusted by the design circuit engineers. Okay, so from this expression, which expression we are talking about, this expression, it is clear that the power dissipation will increase significantly as the value of the load resistor is reduced, and power dissipation will decrease as our RL is increased. Okay, now first of all, let us tell you why it is a wrong idea of selecting a resistive load. I mean, what are the limitations of resistive load circuit? In integrated circuit design, we wherever possible, we use resistors minimum, because in terms of a layout, if you see this structure, serpentine structure, it occupies a very large space. Okay, so since the resistive load involves a resistor, there will be a static power dissipation which is large, which is very bad. Okay, resistor, if they are fabricated on chip, commonly in a serpentine structure for compactness, require a significantly more area than the driver NMOS. So that shouldn't happen. Therefore, a resistive load with a large value of RL is not particularly suited. Why we require large value of RL? I explained you here, right? So that the power dissipation is less, but the large value of RL is not practical because more area will be utilized. Another disadvantage of resistive load is that VOL is never equal to 0. So we have a low voltage output swing always present. We have a poor noise margin. From the examples we have seen, we got 0.993 something. So there is a mismatch between the low noise margin and a higher noise margin. And VTC curve is also heavily dependent upon RL. Okay, and also even if the NMOS driver is off, circuit is still consumes some power because of the resistor. So that's again a negative drawback. So these are all the limitations of why we do not go for a resistive load NMOS inverter. So next time we'll start with CMOS inverter and see its features. We will do its analysis, derivation for all the five critical parameters, and also also solve some numericals. So yeah, that's it for today.